Okay, today's video that we're looking at is the lab on earthquakes, volcanoes, and plate tectonics. So the different lab stations that we have set up here are going to be investigating those topics. The first one is kind of to look at the size and scale of the Earth. And with this one, what we had to do was trace an arc that if we shrunk the Earth down to that size scale, how thick would the crust be, how far above the surface would planes fly, how high would Everest extend off of that surface, how low would the Mariana Trench be. And then after making those predictions and kind of drawing in how high or low we think those things would extend off of the surface, we could then actually calculate to that size scale how high or low those things do really extend off of the surface. The second station that we're looking at is dealing with convection, kind of what happens inside the Earth. So as we look at that second station, what we did was we set up a clear container with a heating source underneath, and we put some ice in one end, and we got the convection currents to start to kind of swirl around inside the container. We were able to put some wood chips on top, and we were able to see the wood chips kind of flow, very small amount, but still were able to flow along the surface of the water, following that convection current circulation. We also used a little bit of dye in there to help us see the water flowing in that pattern. With the third station, we started to look at the math behind the continents drifting and moving, where we were able to see that the continents, if they do move, and not all of them move at the same speed, but they do drift along at about, in our example, 5 centimeters a year. So with that calculation of 5 centimeters a year, we're able to then say that in about 10 million years, some place like Los Angeles and San Francisco, now separated by 500 miles, would be next to each other because of continental drift. Okay, with Station 4, we used a little graphing and plotting of maps to look at the ring of fire. So what we had to do here for Station 4 was kind of plot these different points onto a picture of the Earth, their little map section of North and South America, and we can kind of see where the X's are, there are the earthquakes, and where the triangles are, that's where we're having our volcanoes, and we notice that they follow right along the shoreline, or this part of the ring of fire in the Americas. Then we looked at Station 5, where we looked at the different types of rocks that come out of volcanoes, and we kind of seen that we had a sample of granite, gabbro, basalt, and pumice, along with a piece of obsidian, and then a sixth one there of vascular basalt. Here are the different samples. So we have our granites and our gabbro, a type of basalt, some pumice, obsidian, and finally our piece of vascular basalt. Station 6, we used some magnets to kind of explore the mid-oceanic ridge, or the Atlantic ridge, where we have new crust forming. So we were able to kind of put a magnet around a compass needle and get to see how that part of the ocean floor changes its magnetic fields over time. So here's an example of that lab where we kind of move the compass needle around there, and we kind of see as it flips back and forth in some of those different areas from one ridge to the next. We also get to see some of those ridges have little pairs. So this ridge on the end and on the end here will have the same polarity. The ridges here in the middle will have the same polarity, and the two ridges here on the interior, or the newest pieces here in the middle, will also have the same polarity. So they kind of flip back and forth, so it's going maybe pointing north here, south in here, and then back again to north as it flips, and it'll do the same thing on the other side. The newer crust is forming in the middle of that ridge valley there, and it's then pushing outward on both sides as new crust is forming. And then we went on to Station 7. With Station 7 we are plotting some different points, and with that we kind of look at the earthquakes that are associated with subduction zones. So here's a picture of the paper. We had to again look at the distances and depths of where these earthquakes originated from seismic information, and we can kind of see the line that they start to form as they make this subduction zone, where we have a crust here sinking or diving back down into the earth below a continental crust. Here we also see that it forms a volcano nearby, but we can look at the way the earthquakes are forming there, and that can give us information about where that subduction zone is taking place. So go on here to Station 8. What we had to do here is look at pieces of the continents, and over time those pieces of continents did come together into what we call the supercontinent of Pangaea, and we could see the Eurasian continent here, North America, South America, Africa, India, which isn't a continent but does come up here to form with the Eurasian continent, Australia, and South America. And hundreds of millions of years ago, they were all together as one giant landmass, and over time they've separated into the different parts of the world we see them in today. With Station 9, we looked at volcanic hotspots, and what we did here was we dragged a pen across an index card, stopping at a few places, so it would leave an ink blot in a very similar way to that we see ink blots or the islands forming in the Pacific Ocean. With this map here, we could see how the Hawaiian Islands have been in a long chain forming over the course of millions of years, and as this hot spot in the Pacific Ocean here moves, it forms these islands in the middle of the ocean. Some of the islands don't always make it up to the surface, or some parts that we see here along this island chain may not necessarily make it above the Pacific Ocean, but a lot of the areas do, and as this moves we can see this chain that definitely follows this volcanic hotspot in the Pacific Plate. With Section 10, we were looking at the volcanoes and how they erupt. So we built a model volcano, and we specifically talked about how that model was good and how that model was lacking. So in this model that I have here, I have my little helpers demonstrating how that volcano works, and we could see some of the ways this model works is a good thing, as we see some of the bubbling and gases that are produced when we do this model, which again happens in real-life volcanoes and in our model. Again, the gases that are given off are often very smelly, so we're dealing with baking soda and vinegar, which is definitely going to have a bit of an odor, and real lava will bubble up in that way. Gravity is a force in both, so we see that the volcano does kind of run down the sides there. And some of the ways this model is lacking is it's very cool. It doesn't have any heat associated with it. It happens very quickly as well, so it doesn't take as much time as a real volcano. And for real volcanoes, the materials are not added from above like we did here. Everything for real volcanoes comes from inside the earth. And with real volcanoes, the liquid that we see there hardens into lava. The last station that we looked at, we used some silly putty in a way to kind of determine that the inside of the earth works with molten magma that's sometimes a liquid and sometimes a solid, kind of like oobleck, where when we look at it, it can be a liquid and a solid. So we use silly putty to kind of demonstrate how when we hit it with a hammer, it really didn't change, especially when it was already flattened out. and if we just left the silly putty sitting on the desk on its own, it deformed, or it kind of ran like a liquid very slowly, but it didn't hold its shape. And that's kind of the idea of that lab, is to kind of show that sometimes we could have things that act like a liquid and a solid, and we see that inside the Earth with areas like the asthenosphere just underneath the crust of the Earth there with the lithosphere. If you have any questions about the lab, please stop by in class, and I'd be glad to explain it a little bit more.